Hello, everybody, and welcome back to biosc140 Human Physiology. This is the Energy and Enzymes lecture, S1P5. So, what is energy? What is energy? Energy is the capacity to do work, the ability to do work. Plants use energy from the sun and they store that energy in molecules. So the sun releases a lot of energy. That sunlight, that energy travels through space, comes to the Earth's surface, and plants use chlorophyll to capture that energy and store that energy in molecules. Starch. There's different types, but starch is a main energy storage molecule for plants. Animals cannot trap sunlight. I can't do photosynthesis. Can you do photosynthesis? Probably not. So what do animals have to do? Animals have to consume biomolecules in order to get energy. So plants capture it from the sun. Animals eat plants or other animals to get that energy from the biomolecules. This process of turning biomolecules into energy, which allows us to do work as humans, is not perfectly efficient. It's about 40% efficient. And what do we mean by that? Well, only about 40% of the possible energy that we could get from those molecules, we actually turn into things that can do work. The other about 60% is lost as heat energy. That excess energy, that inefficiency, is lost as heat energy. Excess energy in humans is stored as glycogen and fat. So glycogen is not super famous when it comes to the general public, but a decent amount of energy is stored in glycogen in our liver and in our skeletal muscle cells. And we'll talk about glycogen. We already have talked about glycogen in this class, and we'll talk about it more in the future. It's important. Fat is where most of the general public associates with energy storage, and it's definitely where the most amount of energy is stored in humans. So most is stored in fat, but glycogen is still really important. Before we really move on, I want to talk about why energy is important. Like, why do we need energy? So this kind of goes into physics and the second law of thermodynamics to get to the root core of why we need to constantly consume energy as humans. So the second law of thermodynamics, put very plainly, it says that that entropy is always increasing. It says that the disorder of the world is always increasing. So, and a good analogy is, think about your house. Your house is always getting more and more messy. It's always getting more and more disorganized. And you have to use energy to sweep the floors, to wash your dishes, to pick up your kids' toys and put them away, or your kid has to use energy to pick up their toys and put them away in an ideal world. You have to use energy to maintain the order in your house. Well, that's the universe. The universe is always becoming more disorganized. And as humans, we're a pretty organized structure, right? I mean, you've taken anatomy, there's an organization to our bodies. Well, there's an organization to us at the atomic and molecular level also. And we have to use energy to maintain that order. So entropy is always increasing, disorder is always increasing. We need energy to maintain that order. So Energy is required for processes that distinguish living and non-living things. There are three types of work performed by living things. Chemical. Chemical work is the making and breaking of bonds. The making and breaking of bonds is chemical work. There's transport work. So we talked a little bit about this in the membrane dynamics lecture, movement across the membrane. So this is using an ATP, using an ATPase to move a molecule against its concentration gradient. So transport. Then there's also mechanical, so physical movement, stuff that Arnold here is doing, stuff that Arnold's doing. It's physical movement. Energy, the capacity to do work. It's underlined, it's a vocab word. So ATP is an important source of energy. So our body makes, it eats food and it will make ATP from that food. And then ATP is the molecule that really transfers that energy onto something when we need to give it energy. What I want you to notice about ATP is it's like a compressed spring. We've talked about it a little bit in our second lecture of the semester. You can go back and review if you need to. But right here, I want you to look at these three phosphate groups. We have a negative charge. 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 Do negative charges like hanging out together? No. 4 negative charges right there in this tiny little space. They're held together, but when you break this bond right here, that last one's gonna go shooting off. There's a lot of energy in these bonds, and that last one goes shooting off. It's like a molecular spring. So energy is released when that last phosphate is cleaved. Cleave means to cut right here. So you break this bond, you break this last phosphate group off, and it goes bam, goes shooting off, and it's able to power reactions. It's able to help do work and help reactions move forward. So adenosine triphosphate, ATP. I do use, I'm big on AKAs. I think it's important to know the vocabulary of physiology. You need to know the word ATP and you need to know the word adenosine triphosphate. You can see both of those on the test. Life depends on the ability to transform energy. The ability to transform energy. So we have kinetic energy and we have potential energy. Kinetic energy is movement. Kinetic energy is movement. It's molecular movement, heat. Remember, heat is just the movement of molecules. So heat, the movement of molecules, molecular movement. It also can be organismal. So, kinetic energy, when I'm running, there's energy. When I'm moving, waving my arms around in front of the classroom, there's kinetic energy, there's organismal energy. Potential energy is energy that's stored, energy that could be released. So it's based on location. This person up here has potential energy based on being high up. If he falls or jumps off this board, that potential energy is going to get turned into kinetic energy. It can be based on structure. So look at this structure right here. All these negative charges right next to each other. That structure holds a lot of potential energy or storage. There's potential energy in chemical bonds. So like ATP right here. Also in glucose, in triglycerides, fat. There's also potential energy in, look for like starch and other energy storage molecules in different chemical bonds. There's also potential energy in chemical gradients. And this is a really important concept that I think most people don't really think about until they take a physiology class. but there is potential energy in a concentration gradient. From the membrane dynamics lecture, can you think of an example where we use potential energy, we use energy in a concentration gradient? A synport or an antiport, secondary active transport. You use the potential energy in a concentration gradient and you turn it into kinetic energy, or the movement of a molecule against its gradient. Favorable reactions can drive unfavorable reactions. So energy coupling. Favorable reactions provide energy to drive unfavorable reactions. So let's go back to our membrane dynamics lecture again. Molecules want to move down their concentration gradient. In some situations, we need to move molecules against their concentration gradient, like the sodium-potassium pump of nerve cells. We need to move sodium and potassium both against their concentration gradients. That is an unfavorable direction, an unfavorable reaction to move those against their concentration gradient. So what do we need to do? We need to couple that reaction, that movement, with something that's favorable. So the binding of ATP to that transport protein. Favorable reaction involving the breaking off of this last phosphate, which gives the energy, which does the work that allows the transport protein to work. Unfavorable reaction helps favorable reaction helps unfavorable reaction happen. Energy coupling. So right here, ATP gets recycled. ATP gets recycled. So this circle right here is another example of energy coupling, really. So we have an ATP molecule right here. We cut off the last phosphate and we combine a water molecule also, and we get energy for cellular work. We release energy and we're left with an inorganic phosphate and ADP. ADP is also a vocab word. You should know it. It stands for adenosine diphosphate. So adenosine triphosphate, 3 phosphate groups. We cut 1 phosphate off, we have adenosine diphosphate, 2 phosphate groups. We then will use energy from the food we eat, to combine that inorganic phosphate back onto our adenosine diphosphate, turning it back into adenosine triphosphate. So break off the 3rd phosphate, use that energy for cellular work. We're left with adenosine diphosphate. Do metabolism using the food we eat, put that phosphate back on, get adenosine triphosphate again. That's the ATP cycle. Exergonic is a reaction where you release energy. Endergonic is a reaction that absorbs energy. In exergonic, the reactants have higher energy than the products and energy is released. In endergonic, the reactants have a lower energy than the products and energy is absorbed. When we break off that 3rd phosphate, energy is released, it's exergonic. When we put that 3rd phosphate back on, energy is absorbed, it's endergonic. Let's talk a little bit about reactions. So when a reaction moves forward, there's kind of like a point of no return. A point of no return for a reaction to happen, and that's called the transition state. The transition state is the point where a bond is unstable, or the shape, the configuration is unstable enough to, an unstable configuration where with enough energy to break bonds. So it's basically the point of no return. It's the point where bonds can be broken and rearranged. That's the transition state. Once you reach the transition state, the chemical reaction goes forward. So we have AB and molecule AB and molecule CD right here. They're happy. Energy is put into this system in some way. Those bonds start to get stressed, and those bonds get stressed and stressed and stressed. They start to get contorted, and eventually they're at a configuration that's so unstable that it can break the bonds between AB and the bond between CD. That's called the transition state. We will then have a rearranging of bonds, and we'll end up with our products. The activation energy is the energy required to reach that unstable configuration. Activation energy is the energy required to reach that point of no return for the reaction, that unstable position, configuration. And the activation energy is actually what determines the rate at which a reaction takes place. The rate at which a reaction takes place. So a lot of reactions, how many chemical reactions take place in our body? A lot. And being able to control the rate of those reactions is very important. And we do this by altering activation energies. And how are we going to alter activation energies? Well, enzymes. But let's look at this example first. So right here, we have sucrose. Sucrose is a disaccharide. When sucrose is in water, if you just leave sucrose in water, it will take a very, very, very long time for that sucrose to just naturally break apart into glucose and fructose, its two monomers. A very long time. But if you put sucrase there, an enzyme, it happens super rapidly, very, very rapidly. So what enzymes do is they accelerate the rates of reactions by decreasing the activation energy. So a few more things about enzymes. Enzymes, they accelerate the rate of reactions by reducing the activation energy. They are regenerated. So by regenerated, I mean that they might change shape, they might wiggle, alter a little bit, but after it's done catalyzing a reaction, it's back at its normal state and it can be used again. So the beginning form and the final form are not any different. And there's specificity to enzymes. Some enzymes are hyper specific and only catalyze one super specific reaction. Others are more general and they just break peptide bonds. They break the bonds between amino acids and nothing else, but they'll break a bunch of different types of peptide bonds. So there's varying specificities when it comes to enzymes. When it comes to enzymes, there's kind of two models. There's like a lock and key model where it says the substrate, the sucrose, will fit perfectly like a key within the active site of the sucrase, and that will cause the reaction to take place. There's another model called the induced fit model, which basically says that sucrose and the active site of sucrase, they're going to match, but not like perfectly. But that imperfect match is going to cause a shape change in sucrase and cause a shape change in sucrose. And that little wiggle, that little shape change is going to help help lower the activation energy, which leads to the reaction being catalyzed. And there's actually more evidence for the induced fit model, where things kind of wiggle a little bit and bonds get bent, and it leads to this decrease in activation energy. All right, so reactions have various net changes in free energy. So free energy is kind of just the energy within the bond, within the bonds. So right here, you have an irreversible reaction where there's activation energy and then a large loss of energy. So the loss of energy is so large that without extra energy input, the reaction cannot go backwards. So without a large amount of energy input, the reaction cannot go backwards. One favors one direction. The free energy of the reactants does not equal the free energy of the products. With some reactions, they're reversible. And reversible reactions proceed in both directions. So A turns into B and B turns back into A. A turns back into B, B turns back into A, and it happens all the time. Water is a good example of this. With water, you know, you have H2O, some H3O, some HO, and they all kind of reversibly change back and forth within a glass of water. The energy of the products and reactants, they're not perfectly equal, but they're equal enough, they're close enough that it can happen back and forth in all directions. So reversible reactions obey the law of mass action of the Chatelier's principle. So I want you to take a few moments and look at this slide because you really have to think about this one. So right here we have everything at balance. We have A plus B turning into C plus D, and C plus D turning into A plus B. The rates are equal. We're then going down into the B slide and we're going to add more A. So we're adding A to the system. We have a jar that looks like this. We add A and B to the jar. Well, because we have more AB, the rate at which AB turns into CD is going to increase higher than the rate at which CD turns into AB. And so we're going to have more AB turn into CD than CD turning back into AB. And that's going to proceed until we get back to an equilibrium point. Proceed until we get back to an equilibrium point. Now, what if we remove product? What if we removed 6 squares of CD? Well, if we removed 6 squares of CD, the rate at which CD turned into AB would be decreased. And the rate at which AB turns into CD would remain the same at the initial moment. So we would have more product made, which is CD. So metabolism. Metabolism is the total sum of all chemical reactions in an organism. There are two classes of metabolic reactions. There's anabolic, which is biosynthetic, so life-creating, and that's where you join molecules together to create larger ones. It consumes energy. You use energy to connect molecules together and to form larger biomolecules. The way I remember this is what type of steroids do some baseball players and athletes take? Anabolic steroids. They want to get big and strong. They want to build more muscle, build more macromolecules. So anabolic steroids, anabolic is putting molecules together. Catabolism or catabolic is degradative. It breaks down larger molecules into smaller molecules and it releases energy. All right, so enzymes lower the activation energy. Enzymes are catalysts, so they're regenerated and they're the same at the beginning and the same at the end, and they exhibit some specificity for substrates. I'm going to end part 1 right here. I'll see you in part 2.